In the last video, we introduced the concept of energy. In this video, we'll look into some of the implications of this and develop a mathematical formulation of the law of conservation of energy. We provided a first definition of energy, the ability to do work. Here, we see a falling ball. Initially, it is elevated, which means it has gravitational potential energy. But as it falls, it is clearly losing height, which means it is losing gravitational potential energy. At the same time, we observe it accelerating, which means it is gaining kinetic energy. So, two changes are taking place simultaneously: a loss of potential energy and a gain in kinetic energy. Next, let's revisit this animation from the last lesson. The blue ball is initially elevated, so it has potential energy. But as it falls on the seesaw, it pushes the seesaw over a distance, so it does work. But now look at the ball. In the process of performing work on the seesaw, it has ended up on the ground. It has no potential energy left and very little kinetic energy. It lost energy by doing work. Conversely, the block was pushed through a distance. Work was done on it. It was initially stationary, but later it was moving. In other words, it gained kinetic energy. It's almost like the ball lost energy by transferring it to the block, which gained energy. In the earlier video, we talked about energy as the ability to do work. But this example shows something more. Doing work necessarily changes the energy of an object. Here are some important observations illustrated by these animations. First, energy can be turned from one form to another, like potential to kinetic or vice versa. Second, as the amount of one form of energy increases, the amount of another form decreases. And third, the only exception to that second point is that an object can gain energy through work being done on it, or it can lose energy through a different type of work being done on it, work by a different force. This brings us to the second way of understanding energy. Energy is a characteristic of every object, and that amount of energy can only be changed if it experiences work. Let's take these observations and express them mathematically. Let us say that you examine an object at two different points in time. If you take the total amount of energy something has at the first point in time, that's kinetic energy plus potential energy, and then you add the energy gained through work, and then you subtract the energy lost through work, then you'll have however much energy is left over, kinetic plus potential. It's actually pretty simple. It just says the total amount of energy you started with plus the energy gained from work minus the energy lost through work equals the total energy at the end. This is the law of conservation of energy, and it is one of the most important laws in all of physics. It basically says you cannot create or destroy energy. You can only turn it from one form to another. Let's see how we can use this equation in practical examples. Let's revisit the falling ball from earlier. Let's say we want to determine its velocity just before it hits the ground. We'll assume its mass is 3 kilograms and it falls from a height of 2 meters. We'll start by writing out the full equation of conservation of energy. Point 1 for the ball is the instant where it rolls off the shelf. Point 2 is an instant before it hits the ground. Now, let's cancel out all the terms we don't need. Initially, the ball isn't moving, so we can eliminate KE1. Besides gravity, there is no force acting on the ball that can do work, so work in and work out are eliminated as well. Finally, the ball has virtually no potential energy at point 2. So that leaves us with potential energy at point 1 equals kinetic energy at point 2. Now, let's expand these with the definitions of potential and kinetic energy, and then substitute in all the information that we know. The only unknown is the velocity just before the ball strikes the ground, and it is easy to solve. It has a value of 6.26 meters per second, and we can confirm this result using our familiar kinematics. In this animation, we see a golfer putting a golf ball. Let's figure out how quickly the ball travels immediately after the swing. Let's say the golfer applies 400 newtons of force and the ball is in contact with the club over a distance of 0.2 meters. We'll assume that the ball and the club move horizontally during this time. The ball has a mass of 0.05 kilograms. In this case, the ball has no energy at the beginning, so KE1 and PE1 are both 0. But the club does do work on it. By contrast, there is no opposing force to sap energy away from the ball, so work out is 0. And the ball does not change height over the course of the swing, so PE2 is equal to 0. We are left with work in equals KE2. And from here on out, it is an easy calculation to show that the final velocity of the ball is 56.57 meters per second. Here is a slightly more challenging puzzle. An 80-kilogram object is being moved up a 5-degree ramp. Our protagonist is applying a force of 40 newtons. Initially, the object is moving at 1 meter per second. How far up the ramp will it move? Let's call the bottom of the ramp point 1 and the highest point of the object point 2. Initially, the object has no potential energy, and we're ignoring friction, so there's no work out. At point 2, the object is not moving, so there is no KE2. That means the initial kinetic energy, KE1, plus the work that our hero puts into pushing it, work in, is equal to the potential energy that the object has at the end of the story. Let us expand these all out. It becomes a matter of mostly substitution. The thing which is necessary to realize is that the height and the distance that the object travels along the ramp can be directly related to each other using trigonometry. Since h is opposite the angle, h over delta x equals the sine of 5 degrees. So h is equal to delta x times the sine of 5 degrees. We substitute this into the equation so far. From this point onwards, it becomes a matter of algebra. And we end up with a delta x of 1.41 meters. The object, in other words, moves 1.41 meters up the ramp. This puzzle could have been solved with forces and kinematics, but it would have taken longer. By the way, this solution is a bit of an oversimplification. We'll see a more correct solution when we begin our chapter on rotation. Now, let's consider a roller coaster falling from a height of 50 meters. Or maybe you consider it, I'm scared of heights. If the roller coaster has a mass of 250 kilograms and we ignore friction, how fast will it be traveling when it reaches ground level? This is straightforward to solve. Initially, it's not moving, so there's no kinetic energy at the beginning. It does have potential energy, however. We are ignoring friction, so there's no work out, and there's nothing to push it besides gravity, so there's no work in. At the end, it is at ground level, so there's no potential energy at the end. That leaves us with potential energy 1 equals kinetic energy 2. Substituting all the information that we know, we end up with a final velocity of 31.3 meters per second. Now next, what if there were friction? In this case, there is still no kinetic energy at the beginning, but there is now work out. The roller coaster is going to lose energy through friction. There is no potential energy at the end. So conservation of energy now becomes the initial potential energy minus the energy lost through work out through friction is equal to final kinetic energy. When we expand this out, we find that there are some terms which we don't know. For example, we don't know the strength of the friction force, nor do we yet know how far the roller coaster traveled. So what we first have to do is to find out how big the friction force is, and for that we need more information. Let's say that the ramp had an inclination of 30 degrees and the coefficient of kinetic friction is 0.01. We can set up a free body diagram, sort of like what's shown in the right side of the screen, and we can calculate first the normal force and second the friction force. We end up with a friction force of 21.24 newtons. And by using a similar technique to what we did in the previous ramp problem, we can find out how far the friction force gets exerted over. The object moves over 100 meters, so the friction force is felt over 100 meters. Using this information, we can take this and put it back into the conservation of energy equation which we left on the left side of the screen. We can solve for the initial potential energy, and we can solve for the work done by friction, the amount of energy lost through the work that friction does. By putting these together, we can quickly find the final velocity of the roller coaster. It winds up being a little bit less than before, 31.05 meters per second. In this video, we saw several examples of how to solve conservation of energy problems. We first saw the equation for conservation of energy, which states that the initial amount of energy plus energy gained through work minus energy lost through work equals the final amount of energy. And we saw several examples of how to use these in practical applications.